Bismillahirrahmanirrahim. Assalamu alaikum everyone. In this tutorial we are trying to learn and implement interrupt implementations, right? So interrupt for PIC18F microcontroller, we are going to test them in Proteus and MPLAB environment. So let's consider an example for which we will be using interrupt, right? So we are using PIC18F452 microcontroller, and we will be using external interrupt, which is int0, int1 and int2. And if you talk about specific pin numbers, so basically interrupt 0 is dedicated to RB0 pin, interrupt 1 is dedicated to RB1, and interrupt 2 is uh, RB2, right? Similarly, RC0 is a pin uh, where we are generating a square wave, right? A square wave of 500 hertz. So we will be producing a square wave of 500 hertz. And this time we know that for 500 hertz, we need to, for a square wave, we need to turn on and turn off this RC0 uh, respectively, right? Progressively. So what we do, we will use a timer here, and in this example we will be using timer as an interrupt, right? So there will be an interrupt whenever timer expires. Microcontroller will go and toggle this LED and then come back to the main code, and again when timer expires, microcontroller will go back to this LED and toggle this LED, and so on, right? So interrupt 0, interrupt 1, interrupt 2, external hardware interrupts are basically age triggered interrupts. We have already discussed in theory lectures, right? So interrupt 0, interrupt 1, interrupt 2, both are basically age triggered. So they can act, sorry, all three of them are age triggered. So they can be triggered on negative age and on positive age. By default, every one of them is positive age triggered, but we can make them negative age triggered. So we will use them. Uh, this interrupt 0 and interrupt 1, we will use them as positive edge triggered, right? And interrupt 2 we will use at negative edge triggered. Okay, before we proceed, two other output pins are used, which is RC1 and RC2. Both of them are connected to LEDs, right? So what our program will do, whenever interrupt 0 appears, that means external interrupt has appeared at RB0 pin, right? And it is positive edge trigger. That means there will be a positive edge. It will be, there will be a transition from 0 to high, right? So what going to happen? Microcontroller will be interrupted, and microcontroller will turn on the LED which is connected to RC1, right? Similarly, when there is any interrupt on interrupt 1, that is transition from 0 to high, right? It will switch from 0 to 1. So microcontroller will be interrupted, and microcontroller will turn on the LED which is connected to RC2, right? And now, if there is a negative transition, that means it will be initially 1 and it becomes 0, right? So there will be transition from high to low. So microcontroller will be interrupted from interrupt 2, and what microcontroller will do, microcontroller will turn off these both LEDs, right? So interrupt 0 will turn on RC1, and it is positive edge triggered. Interrupt 1 is also positive edge triggered, and it will turn on RC2, right? And interrupt 2 is negative edge triggered. So whenever there will be a negative transition, or you can say falling edge from high to low, so what microcontroller will do, microcontroller will turn off the both LEDs. Okay, before we proceed and see the example of the code, first of all, we need to know that we are interested here to generate a square wave, and a square wave of 500 hertz. So we need to perform certain calculation, and that I have done for you. So frequency we are required is 500 hertz. That means the square wave time period will be 2 millisecond. That is just reciprocal of 1 over 500, right? Then 2 millisecond is total time period. So on time and off time would be 1 millisecond. So for 1 millisecond it will be off, and 1 millisecond it will be on, right? So that means we want to produce a delay of 1 millisecond. And let's assume that crystal oscillator which is attached to this microcontroller is 20 megahertz. So we know that frequency of instruction can be calculated by dividing it 4. So 20 megahertz divided by 4 will become 5 megahertz. And similarly, we know that frequency of instruction is 5 megahertz. So the reciprocal of it will be time of one instruction. So time of one instruction is 200 nanosecond. Okay, we know that time of one instruction is 200 nanosecond and total delay required is 1 millisecond. So the number of iteration or the number of count for which we have to run our timer can be calculated. Required delay divided by time of instruction. So 1 millisecond divided by 200 nanosecond, that means it is equals to 5000. Means we need to produce a count of 5000, right? And timer initial value, what should be timer initial value? So it should be 60536. I have skipped the procedure. You know that the maximum count is what? 65,536. You need to subtract that uh, count from that maximum count, so that you will receive 60,536, and that these denotes it is a hexadecimal. EC78 is what? The equivalent hexadecimal entry, right? If you see, it is now. So initial value was 60,536, and if you convert it into hexadecimal, it is EC78. So for timers, we know that if we have three different registers, so timer 0H will become EC, timer 0L becomes 78. I hope you have already gone through the timer section of this course, and when you are watching this tutorial. So you need to know that we need to program three register in timers: timer 0H, timer 0L, right? Then timer 0 control. Again, there will be various configurations. First 0 shows it's off, second 0 shows it is 16-bit mode, third 0 shows internal source is used, right? Fourth 0 shows it is a positive age count up, right? And then fifth one is showing the prescaler is disabled, and since prescaler is disabled, so all three bits will become 0. So that is in binary, and if you convert in hex, it will become 08 hex, right? So this is one of the uh, very short description of timer calculation, but we will perform also the code. So let's write the code. Okay, let's discuss the code. I have written it for you, right? So we will start the code from the very beginning, right? So let's see. The code is starting here from originate 00. That means we are starting from the 00 memory address in the program memory, and then we have a very first instruction, which is go to main, right? So what we are doing, we are directly jumping to this label main. We will look for this label, and we found it here, main. And here code is starting at originate 2a, right? That means we are starting our main code in the program memory at the address 2a hex, right? Then what we are doing, clear F press C, that means we are making port C as output port. Clear F port C, that means we are clearing all the bits of initially 0 of port C. And then set F press B, that means what we are doing, we are actually making port B as input port, right? Because uh, every interrupt, right? Interrupt 0, interrupt 1, and interrupt 2, they are dedicated in the port B. So these pins will be serving as input port. So in this area, we are just defining our input and output ports. Okay. And next thing, what we are doing, we are actually integrating the values of timer, what we have calculated earlier. Here we have performed various calculations. So move literal to working 08 hex, and we are moving it to timer 0 control, move working F timer 0 control. That means we are feeding this 08 hex into timer 0 control. Then move literal to working 0 EC hex, move WF timer 0H. That means we are feeding EC into timer 0H. And similarly, move literal to working 78 hex and move WF timer 0L. That means we are feeding 78 into timer 0 lower byte. And then what we are doing, VCF interrupt control, comma, timer 0 IF. That means we are clearing timer 0 IF, right? Initially it will be 0, right? So we are making it 0. Okay, then what we are doing, it is something very important from interrupt point of view. We are enabling individual enable of timer 0, DSF interrupt control, comma, timer 0 IE. Okay, just to remind you, I have already explained these things in very much detail. You can go and watch my video lectures on theory sections, right? So one is called interrupt enable, right? Other is called interrupt flag. Whenever certain certain interrupt arrives, what happened that in the that interrupt flag becomes 1. Okay, and by default interrupt enable is 0, right? And then both of these input are passed through a AND gate, and then output goes to uh, main interrupt output, right? But you know that if we have not make this individual enable equal to 1, then if we have interrupt flag high, but it won't proceed to the output. So what we have to do, we have to also make it 1, right? So initially it is 0 and we have to make it 1, and that's what we are doing in this specific line. We are actually enabling interrupt enable of timer 0, and then next 3 lines are dedicated for interrupt 0, interrupt 1, and interrupt 2. So we are enabling their individual enables in next 3 lines, right? So whenever there will be interrupt arrives either from the timer side or from the external hardware interrupt side, so what will happen, we will uh, those individual flags will be ended with their individual enable. What we have already made equals to 1. Okay, the next line is again interesting, and it is related to negative age and positive age of external hardware. We know that interrupt control 2 is a register where 3 bits are very important, which is int age 1, int age 0, and int age 2, right? So these bits are by default 1. That means all these 3 interrupts are positive age triggered, but we want to make interrupt 2 as negative age. So what I'm doing, I'm making this int h2 bit 0. So what I'm writing, bcf interrupt control comma int h2. So it is just to make this interrupt 2 as negative age. So now interrupt 2 will provide interrupt when we have a negative edge on it, right? So this is just for this purpose. And then we know that this is what another important instruction for interrupt mechanism. Uh, though there are individual gates, but they finally arrive to the main output of interrupt, and that main output is again ANDed with another input. If you don't make that input 1, your interrupt won't go to microcontroller, and that is what GIE, right? So you have to make this bit again 1. So what I'm doing in this code is DSF interrupt control comma GIE. That means I'm making that bit 1. So now interrupt, if any of the interrupt will arrive, provided that their individuals was high, right? But they will actually proceed to microcontroller because globally interrupts are enabled, and that is GIE, global interrupt enable. Okay, then what we are doing, we are starting our timer. We have feeded the perfect values in the timer, but it is not started. Remember, this value, this starting value is what? 0. 0 means timer 0 on bit is off. So we have to make it 1 so that timer starts. So we are making this thing in this line, right? So it is just start of time. And then what we are doing, we are just looping on this line. Branched ABC and ABC is here. Branch ABC, ABC is here. So we are staying on this line unless there is some interrupt arrive, right? So let's say if some interrupt arrives, where microcontroller will go? Microcontroller will go to interrupt vector table, which is what? Which is the address of various interrupt service routines, right? So it is not service routine itself, right? But it is the place where you will find which of the interrupt has interrupted the microcontroller, right? So there are 4 interrupts flag we are checking here: timer 0 IEF, interrupt 0 IEF, interrupt 1 IEF, interrupt 2 IEF. So we check one of them one by one, and if any of them has interrupted it, so it will be high, and we will go to its respective interrupt service routine. ISR is what? Interrupt service routine for timer 0, interrupt service routine for interrupt 0, ISR interrupt service routine for interrupt 1, ISR for interrupt 2, right? So these are just label. You can use any other label. I'm just uh, trying to use a label which is meaningful, right? And if any of these flags are not high, that means there was a false alarm, right? So you have to go back to the main code. That is why I'm using this return command. This is basically not a simple return. It is retfy, return from interrupt enable, right? So whenever microcontroller will be going to this interrupt vector table, right? So what it will do, it will make this GI bit equals to 0. That means because he is going to already serve one of the interrupt, so he cannot entertain any other interrupt. So that is why GIE is disabled, so that there won't be any further interrupts, right? But we have realized that that was a false alarm, so we are returning back to the main code, so we need to enable it again. So this retfi instruction enable does do the both things, right? What it will do, it will return to the main code and it will also enable this GIE. So that is why I'm using retfi. Okay. Furthermore, if any of these interrupt was real alarm or was really there, so we have to go and serve their interrupt service routine, right? So the third section is written for this specific code, right? That is for timer 0, and again you can see that at the end there is a retfi. This is for interrupt 0, this is for interrupt 1, and this is for interrupt 2. So let's see them one by one, right? So if you see the timer 0 interrupt, what we are doing, first of all, we are turning off the timer, then we are toggling the bit, this RC0, right? Then we are feeding these values again, EC and 78, and then timer 0 IF, which have become 1 due to interrupt, so we make it 0 and then again start the timer and retfi to main the code, right? So I hope you have understand this timer 0 service routine. What we are doing in interrupt 0 service routine, remember, whenever interrupt 0 arrives, what you will do, you will turn on this LED. So that's what we are doing, BSF port C, 1, and then the flag is becoming again 0 and return 5. I hope it is very clear, because we are just doing two things. First of all, we turn on the respective LED and uh, clear the flag, and that's what we are doing in interrupt 1 as well. ESF port C, 2, and VCF interrupt control 3, int 1 IF, right? So we are just turning on the respective LED and clearing the flag. And what we are doing in interrupt 2, remember, interrupt 2 is designed to clear the both LED or to turn off the both LED. So we are turning off the both LEDs and then clearing the flag of the respective interrupt and retfi. That means we are returning to the main code and also enabling the interrupt. I hope this code is much clear and you can easily understand it now. If you have any query, you can post your queries in comment section. Let's go to the MPLAB environment where we will actually compile this code in assembly code and then we will burn it into the Proteus. It's almost the same code. I hope you can see it. It's a similar code. I've just written it here, and what I have to do, I have to just compile it. Remember, these 4 lines or these 3 lines are just included just to make a hardware configurations right into the microcontroller. We have already discussed it in the previous tutorials. I hope if you are following my series, you are quite aware about these lines. If you haven't, please watch the previous tutorials, right? But these are just 2 lines. Otherwise, the main code is all, I have already explained the code, right? So I will just compile it. Build succeeded. That means its code is working. Now what we have to do, we have to burn this hex file, the hex file which this assembly has generated into the Proteus environment. So let's go to the Proteus environment. Okay, this is the Proteus environment I have created for you, and I will build the code from the hex file. Remember, 20 megahertz is a crystal oscillator that I'm using, and that is the hex file I have to use. I will upload it. Okay, it is uploaded. Okay, I will explain it, but I need to make certain annotations for you first. So this is a section. This push button is basically simulating the effect of interrupt 0, right? And this push button is simulating the effect of interrupt 1, and this is interrupt 2. So if you are observing it clearly or closely, you need to watch these connections. Look, RB0 is connected to this point and this is grounded with this resistor, right? And then this edge is connected to this specific VCC, right? So whenever I will push this button, what is going to happen? This RB0 will be connected to this VCC. Otherwise, this RB0 is grounded. So initially it is 0. If I press this button, it will become 1. So there will be a transition from low to high, right? So this is what, this is a low to high transition or positive edge trigger, right? This is interrupt 0. Let me write it for you. That is our interrupt 0, and uh, that is a positive edge, right? And the next one is interrupt 1, and it is also positive edge because it is also connected in the similar fashion. Look, RB1 is connected to what? This grounded directly, and if we push this button, that means it is connected to VCC. So it is also what? It is also having a low to high transition if I'm going to push this button, right? But the case is different for the RB2. RB2 is connected to this pin, which is connected to what? VCC. That means it is initially 1, and if I push this button, it will be connected to what? Grounded. Why I have used here resistor? Because if I will push it, both of the point will be connected. So it will again remain 1. But I have made this one path or VCC path resistive. So I have connected a resistor here. So that will be high resistive path, and that will be low resistive path to the ground. So it will go to the ground. So initially it is high and it will go to the low when I'm going to press it, right? So this is what interrupt 2, and it is a negative age trigger. I hope this point is clear, and this is very important, right? What I've done otherwise quite simple. One LED is connected to RC1, another LED is connected to RC2, and this RC0 is going to this oscilloscope, which will be showing us what? The square wave which we want to observe. Remember, we will have a square wave using the timer 0 interrupt, right? So I hope this connections are quite clear to you now, and now I can easily turn on this simulation. So I'm turning on this simulation. Okay, this is the oscilloscope that I wanted to show you. Look, this is the 1 millisecond division. So every box is about 1 millisecond. So if for 1 millisecond it is on and 1 millisecond it is off, that means the time period of a square wave is what? 2 millisecond. And that was the time period of required wave. So the wave frequency is what? 500 hertz. So that is just one thing. Okay, I can just close it just to uh, clear to see the effect of interrupt 0. So now interrupt 0 is what? Positive age triggered, and it will turn on this LED which is connected to RC1. So I am going to press it. There is right now it is 0. It will become 1 when I'm going to press it. So see, there was a positive age transition and LED is turned on. If I am going to press this interrupt 1, what is going to happen? This LED is on. And if I am going to press it, this is going to, it is initially connected with VCC and it will be turning on to low. So let's see what is going to happen. Both LEDs are off. If I press this button, this LED is on. If I press this button, all the LEDs are off. I hope this point is much clear. Okay, I don't see my oscilloscope. If I stop my simulation and start it again, it is not coming. I've already explained it in previous tutorials, but since the point is quite easy to explain again, so I can explain you. Once you cross the any dialog box in running simulation, it won't reappear if you start again, right? How you can make it appeared? You have to go to this debug option, and there are various things like digital oscilloscope and some other stuff. But I am actually turned off what digital oscilloscope, so I will turn it on again. So if you cross it, how you can bring it back? Go to debug and press this digital oscilloscope. You will find it, that option. Whatever you have crossed, you will find that option. So I hope this tutorial is much clear to you, and now you can easily see this simulation is working according to your requirements, right? I hope everything is clear. Still, if you have any confusion, you can post your confusions in comment section. Thank you so much for listening.